Let's consider net force for a minute. If I consider net force, there are how many forces acting on the meter stick right now? Can you name one of them? So gravity is one of them. This would be the weight of the meter stick. What's another one? Tension. But I think there are two tensions, don't you?
Yeah.
Tension on the left and tension on the right. Does that make sense? Any questions about that? Is the net force on the meter stick 0? Is it going anywhere? I mean, you can just look at it and tell me the answer, right? If the net force were not 0, it would not be sitting still. So can we all agree net force is 0 on a meter stick?
Yep.
Well, that would mean that T left plus T right minus the weight of the meter stick has to equal 0. So I don't think the weight of the meter stick is 0.46 or 0.45. Do you? If I look right now, I'm seeing 0.45 and 0.45. I know it's fluctuating a little bit, but I'm just going to go with 0.45 and 0.45. Seems to tell me that the weight of the meter stick is 0.9 newtons. Any questions about that? Pretty straightforward. Now, here's what I want to do. You'll notice I have a string I've hung here. I want to place this 500-gram mass on the string, but I'm going to notice it's closer to one side than the other. When I place this mass on the string, do you think both of these will be pulling up with the same force? Do you think one of them will have to pull up more than the other? This one? So what I want to do is I want to talk about how would we predict how much force one side would experience versus the other. Right? I don't want to build the bridge and then find out that it can't hold the stuff, right? So we're going to try and predict how much tension is on this side when I place this on my bridge. And I've taken the answers off because we want to see if we can predict it ahead of time and then get our answers. So I'm placing 500 grams and it's at the 30 centimeter mark, all right? So this is going to be our sample question. First, can we agree that this is a net force equals 0 problem? All right. So I'm going to have, let's see, it's on the left. There, does that look good? Over on the left, and this is at the 20. This is at the 30. This is at the 50. And this is at the 80. I'm just putting where all those forces are acting. In statics problems, oftentimes we're tasked with using Newton's first law. So we've talked about Newton's first law for forces before. We just used it a minute ago. We're going to use it again here. I see 4 forces. Do you guys see 4 forces? So let's start by just listing out our forces. I'm going to make upwards positive. So net force equals 0. I see tension on the left, upwards, minus, all right, this is a 500 gram mass. So in order to be in appropriate units, I want to put that as a weight, and I have to put it in newtons. So 0.5 is the mass times 9.8. Now it's in newtons, mg. All good? So I want you to be able to do this on your own, getting everything in the same units. Next, we know the weight of the meter stick. We just measured it it's 0.9 newtons. So I'll put 0.9 there. And last, I have one more force. It's acting upwards. It's the other string, right? So plus tension on the right. And all of this has to equal 0. Well, the very first thing I want you to see is there's no way to figure out from this alone what one of the tensions is, right? I have two unknowns and just one relationship. The best I can do is tell you what the combined tension is, but I can't tell you how big one of them is versus the other. Do you guys see that? That's why we have to use both net force and net torque. Net torque can help us narrow this down. Because if we look, the net torque is clearly 0 as well, right? It's not rotating or spinning. And although I don't know where the pivot point of the system is, I know if I pull hard enough here, this will become a pivot point, right? If I pull hard enough here, this will become a pivot point. So there are some natural pivot points already here, and if we were to place too much force on one direction than the other, it might begin to pivot. Does that make sense? So I want to talk about how we set up the pivot point part of this. I'll put this on the ground so it's out of the way for our work on the board, but then we'll come back to it, okay? To do a net torque problem in a situation that is static, like this one, there are several things we can do at the onset of the question. First, we have to clearly articulate that we believe the net torque is 0. Right? Also, there's one other thing that has to be true before we can do what we're about to do. The velocity has to be 0. And I mean both velocities, the linear velocity and the angular velocity. The reason why we have to establish this is because we have to establish before we start the problem that there is not a known pivot point. If it were spinning, it would be spinning about some pivot point. So we're establishing before we start that there's no pivot point. The reason that's important is that means we can choose any place we want to be the pivot point. Put that in your notes. Step 1. In a statics problem, we choose where the pivot is. Only if omega is 0. So step 1, we choose the pivot. If the angular speed is 0. If it's spinning, there will already be a pivot point. You can choose anywhere on this object to be your pivot, anywhere you want. Now, if they give you the pivot you have to use, then you have to use the pivot they give you. There's just no way around it. However, if they don't give you a pivot, you can choose places that will probably be better than others to be your pivot. I want to remind you about something you're about to do. You're about to calculate individual torques. And individual torques require a torque arm, a force, and the sine of the angle between them. Right? That's how we calculate a torque. If we're careful, we can choose pivot points that reduce how hard our problem is. For example, if I placed a pivot point here, well, I've made all my measurements relative to that point being 0. So they're already there. I don't have to worry about redoing my measurements. And from here, there would be 4 torques because there are 4 forces. So that's not a bad place to go. But if I do this, and you guys, this is where the reasoning part up here, and I'm not going to write down what you need to write down, but you should. If I do this, this will make a new equation that has 2 unknowns in it, right? T left and T right will still be unknowns. And that means we'll have 2 equations and 2 unknowns. We can solve that, but that's complicated, right? You know that means substitution and stuff like that, right? I'll remind you, we can choose anywhere we want to be our pivot, but if we choose this pivot point, we make a more complicated problem.
there are better pivot point choices. Since we can choose anywhere, if we choose the pivot point to be at the location of an unknown, right? If I choose to put the pivot point where one of my unknown forces is, the torque arm length there is 0. So I don't have to worry about that torque at all. I eliminate an unknown from the equation. Again, I can put the pivot point anywhere, but the best place to put the pivot point is something that will simplify the equation. Place the pivot point at the location of one of your unknowns. Place the pivot point at the location of one of your unknowns. If I place the pivot point at an unknown, this whole unknown doesn't get involved in my question now. I reduce how much work I have. Now I still have 3 other torques. I have the 500 gram weight, I have the weight of the meter stick, and I have the tension on the right. So I still have 3 torques. So I'm going to set up a grid. Torque for the 500 gram mass, torque for the meter stick, and torque on the right. Bless you. 3 torques. Each torque has a torque arm, a force, and the sine of the angle between them. I'm setting up a chart. Can you kind of see the beginnings of this chart? I want to add them up and set them equal to 0. Net torque equals 0. So that's what I'm doing. I'm adding all of these up and setting them equal to 0. Everything all right so far? Remember the right-hand rule from Friday? So do you want out of the board to be positive, or do you want into the board to be positive? Makes no difference to me.
Out of the board.
Out of the board's positive? All right. I didn't tell you this, I don't think. The symbol for out of the board? Oh, I did? So the symbol for out of the board is this. We're saying out of the board is positive. Out of the board is anything that rotates this direction. Or if you want, do we do the 3-finger rule? So let's look at our first torque, the 500 gram torque. Torque arm is from the pivot point to the 500 gram mass. So I'm pointing to it. My middle finger needs to point in the direction of the force. So this torque is this way. It's trying to get the meter stick to rotate down that way. Would you agree? Follow what I'm saying? And this is into the board. So this first torque is negative. Now guys, if you just want to say clockwise and counterclockwise or something like this, that works just fine. I'm showing you the way that, the whole complicated way, but clearly this force is trying to get it to turn this way. This force is trying to get it to turn this way. And this force is trying to keep it from going that way. You see that, right? So you don't have to make it super complicated with the hand gestures. I'm just showing you how the hand gestures work. Now let's do the math on this one. It looks like the torque arm length is from here to here, 10 centimeters. So I'm going to do 0.1 meters. Size of the force is 0.5 times 9.8 mg. And you saw the picture, and you saw the actual thing. Can we make it pretty clear that the meter stick is horizontal and the weight is pulling straight down?
Yes.
All right. So I'm thinking we're talking about a sine of 90 degrees. Let's move on to the meter stick. Can we see it's also negative? Right? It's trying to get to go in the same direction as the weight. Our torque arm, though, is from here all the way to here. How far is that from 20 to 50? 30. So 0.3. The weight of the meter stick was 0.9 newtons. So I already have it in newtons. And I think it's pretty clear, also sine of 90 degrees. Last one. Right-hand rule for this one. Torque arm this way, force upwards out of the board. Trying to get it to rotate that way. All right, so this one's positive. And look, one had to be positive, one had to be negative. That's the only way it's going to work, right? So positive. And how far is it from 20 to 80? 60. So 0.6. We don't know the size of this force. Sine of 90 degrees. I'm stopping for a minute. Now the math on this isn't particularly tough. We're just going to add these things together. 0.5 times 9.8. You guys know what that is? You got calculators, right? 4.9. And then times 0.1. Can you do that part? Come on, do something. Have something in here. So it's going to be negative 0.49 is the first one. All right. Minus 0.3 times 0.9. And then I have plus 0.6 TR. And that equals 0. All good? All right. Let's get TR. Hop to it. You guys got calculators. I'll pick one of you. What do we got?
I got 1.26.
1.26? All right. Thank you. Now, we're supposed to get both of them. We only have one of them, but you should have a way to get the other one, right? We wrote out something that would help you get the other one already. If you don't know what I'm talking about, right here, it's how to get the other one. So we're going to take this, throw it there, figure out what T left is going to be. So right, we know what the answer, we can check the answer, right? We've kind of set this one up, so we're going to check it. Let's see what we got.